All right, so let's look at an example that kind of encompasses or utilizes all these ideas and kind of see how they might interplay. So let's say that we've got uh, a couple signals coming in, and the signals are vectors, meaning that they consist of multiple bits. Um, and let's say uh, we've got a 2-bit signal coming in. So I'm just going to draw two wires, meaning that there's two signals going through here. And we'll just call it X. And let's say we've got another one. We're going to say Y. And we want it to be the least significant bits of our final number. We're going to be putting some stuff together if you haven't noticed. And then we're going to have Z. And the thing with Z is it's also going to be a 2-bit vector, but we need to flip the bits. So what I'm going to do is I'm going to make something like that and make something like that. So now the least significant bit is now the most significant bit. And then Z in total, those bits are the most significant bits of our final number, and we'll call our final number A, where this is our least significant bit now, and that makes this our most significant bit. So we're going to have to make a module that brings these X, Y, and Z in as inputs, outputs A, and arranges things properly. So yeah, let's give it a try. And it looks like for this example that I just came up with the top of my head, we're actually not going to need a wire, but if we did, the syntax would be the same. The reason why I say we're not going to need a wire is because A is just going to be an output. It's not going to be an intermediate thing. It's going to be input and output. This module is just kind of rearranging bits. So let's give this a shot, eh? All right. So of course we're going to have module, and we'll call this thing a rearranger. And so what are our inputs going to be? Well, we're going to have X, Y, Z, and out. And put an end module there. And so remember, we don't list the sizes here, right? We list the sizes when we declare our inputs and outputs. Oops, don't forget your semicolon there. I always do. For me, it seems like a weird spot to have a semicolon, but whatever. All right, so let's list our inputs first. So X, Y, and Z are all 2-bit vectors, so that means that we can make them in the same line. And so 2-bit vectors, really we could put any numbers here as long as they differ by just 1, really. 1 and 0 here. And remember, to compute the size of this, it's just your max index minus your min index plus 1 to find the size. So that means we have a bit 0 and a bit 1. And let's list X, Y, Z there. All right. Now let's do our output. And what do we have here? We're going to have, just to make this look a little nicer. So how many bits is this? This is going to be 6 bits. So that means we're going to do 5 to 0. Right, so 0 through 5 is 6 bits, right? And that is going to be named output. All right. Now, when we want to do our concatenation, I'm not going to do it in a procedural block. I'm just going to do it kind of out in the open, right? And what I mean by that is I'm going to use an assign statement. So I'm going to assign out equals, and now here's where I start doing my concatenation. When I use these curly braces like that, That's when I'm doing my concatenation. And now let's go back to my sketch real quick. So the most significant bit right here, this is going to be the way we've got things addressed. Let's go to a different color. This is going to be Z, and we need to index just this single bit, which is Z0. So that means this one is Z1. So let's do that there. So we're going to say Z0. So that's just pulling out one bit of the Z vector. And then the next one is Z1. Remember that this place in your concatenation means it's your most significant going down to your least significant. All right. Now, Y is next, right? If I call correctly. Oops, nope, sorry. X is in the middle. Lucky I checked here. And since I'm not stripping bits away from the X vector, I can just put X in there. Just like that. Don't need to have any indexes or anything like that. I could, however, I could say 1 through 0, and that would be the same as not having anything there at all. So I'll just put it there for example. And it looks like the last bits that we have here are Y. So let's put Y in there. And there we go. So we made the Z bit's the most significant, and we flipped the most significant of Z with the least significant. We put X in the middle and Y at the end. And so this is going to kind of just take these and rearrange them. Concatenation can be really useful when you're dealing with things in parts and you have to put the parts together later, or you have to reference certain parts of bits or a bunch of certain parts of signals. And obviously vectors are very useful because we want to be able to deal with big compound things. Vectors are also useful if, say, you're doing kind of a conventional circuit where you get a bunch of single bit signals, but you want to use a case statement. It can be very handy to take all those single bit signals and crush them into a multi-bit vector so you can deal with each case as a decimal number rather than bit by bit by bit.